So to design convnets, first let's understand this concept called convolution. And we'll understand this concept of convolution from the perspective of edge detection. Remember, edge detection is what our V1 or primary visual cortex, our primary visual cortex, actually detects edges, right? Edge detection is one of the simplest mathematical operations, and we'll first learn this, then we'll build new things, right? And I'll also introduce you to the concept of convolution from the perspective of edge detection. So let's actually take a nice simple example, right? So let's take a 6x6 image. Okay, so let's assume I have an image like this. Okay, let's assume it's a 6x6 image. Okay, and let's assume there is a region of the image like this, which is fully dark. Let's assume this region is black. The lower half of the image is dark, right? Lower half of the image is dark and upper half of the image is white. Okay, so this region is white and this region is black or dark, right? Now in this image, if I ask you, is there an edge in the image? This is a very small image, it's a 6x6 image, okay? If I ask you, is there an edge in the image? You would obviously say yes, there is an edge here because everything above this edge, and it's a horizontal edge, you would say this is a horizontal edge because everything above this edge is of one color, everything below this is of a different color, isn't it? So you would say that there is an edge here. Now our goal is, given this, we'll take a simple example of a 6x6 image, okay, and we'll take a simple example of a grayscale image. We'll come to color images later. A simple grayscale 6x6 image, and we'll learn how to detect a horizontal edge like this, right? We'll see how to detect it. Let's understand what is the input and what is the output. The input is this simple 6x6, 6 pixels by 6 pixels image. So let me just expand the 6 pixels by 6 pixels so that I can explain you what is happening here. So 4, 1, 2, 3, 4, 5, 6. Okay. So 1, 2, 3, 4, 5. So this is my 6x6 pixel image, right? So let's actually write the pixel values, right? Because the lower bottom are all black. Let's call all black pixels as having a value of 255. Let's just say I can call black as 255 or white as 255. It's up to me, right? So all these values are 255, 255. It's a grayscale image, right? So grayscale image basically means that it has values between 0 to 255, right? So I'm just putting in all these values, okay? 255, 255. So 255, 255. Okay, let me just write down 255s just in a quick. So whenever I say 255, again 255. So wherever 255 is written, it means that that pixel is black. All the pixels that are white, I'm just giving them a value of 0. Okay, very, very simplified notation. Okay, so given these images, right, this is a simple grayscale image, right? Of course, you can also scale your grayscale images from 0 to 1 by normalizing the image, because the maximum value is 255, right? And the minimum value is 0. If you do min-max type of normalization, you can just replace this image. All these values will be 0, all these values will be 1, right? Depends on how you're representing your grayscale image. Now, given this grayscale image, I know that everything above, so these pixels are all white and these pixels are all dark. So there is actually a difference in colors from here to here. And that's why my eyes see an edge here, because there is a difference in color between this region and this region. That's why my eyes see an edge there. Now, how do you detect an edge? To detect an edge, we do a simple operation called a convolutional operation. So this operator, when you do it on matrices, is no more multiplication. This is called convolution. This operation is called a convolution operator. Okay, I'll explain you what convolution is and everything in slight detail. It's a very, very simple thing. Now I have an other matrix here. So let's say I have a 3x3 matrix. This matrix is often called as the convolution kernel. Remember, this is not your SVM kernel. This is not your SVM kernels. This is a kernel in image processing. It is often also called as filter. It is also called as mask. There are multiple names to it. It's also called as an operator. Okay, there are multiple names to it. Okay, so it's often called a kernel also. So there are multiple names to this matrix. So this matrix, let's assume I have values like this. I'll explain you why these values and things like that. So let's assume I have a 3 by 3 matrix that has values like this: -1, -2, and -1. First thing you'll notice is the values in the first row are same as the values in third row except for the sign. And the values in the middle row are all 0. Right? Okay. So you have a 6 by 6 matrix. This is, let's call this your input image. Right? What is a task of edge detection? You're given an input image and you want to detect edges. And we detect edges by convolving, or by applying a convolution operator, on the input matrix, because an image is nothing but a matrix, right? You can think of an image as nothing but a matrix of pixels, right? Now, given this kernel or this filter, this is also, there is a special name for it. It's called the Sobel edge detector. This matrix, this 3 by 3 matrix in image processing is called Sobel edge detector. Okay, to be more precise, it's called Sobel horizontal edge detector. Let's see what it does. That's very, very important, right? So you have this matrix and you have this matrix. Okay, so the operation of convolution generates a 4 by 4 matrix. So it generates a 4 by 4 matrix. I'll explain you how it generates it. Okay, let me walk you through this example so that you have much more clarity. And I'll explain you why it creates a 4 by 4 matrix. Okay, and how it creates it. So first it says, this is my orange matrix, this is my kernel matrix or my filter, this is my input image. So I'll first try to place this 3 by 3 matrix on top of this. When I draw a 3 by 3 matrix here, okay, first I will place this 3 by 3 matrix on top of this input image. So I'm placing it here like this. So here I have a value of 0. Here I have a value of +1. So multiply corresponding cells. So 0 multiplied by +1 is 0, right? Plus 0 multiplied by 2 is 2. Sorry, is 0. Sorry, I'm sorry. 0 multiplied by +1 is 0. All three are zeros, all three are zeros. So it will be 0 plus 0 plus 0. What about this? 0 multiplied by -1, 0, 0 multiplied by -2, 0, 0 multiplied by -1, 0. So what are you doing here? You're multiplying corresponding cells. You're taking this cell, this is a 3 by 3, right? And you're multiplying it with this. You're taking this and you're multiplying it with this. And when you multiply all of them, then you add them up. Okay, so this is literally multiplying. So let me write it down. It's basically component wise multiplication followed by addition. Okay, this is very, very important. It's component wise. The corresponding cells will be multiplied. When I multiply it, what is the value that I got? Sum of all of them is 0. So I'll put a value of 0 here. Right? Now let's take, if I take this 3 by 3 matrix, okay, instead of this orange 3 by 3 matrix, right? First I finished this. So when I used the first 3 by 3 matrix, I got one value. For the next value, for this value, what do I do? To fill this value in the matrix, I will shift by 1. And now I will use this 3 by 3 matrix. I'll multiply this 3 by 3 matrix now of values with this matrix. Again, component wise multiplication followed by addition. Even that will result in 0. Let's take a case where it doesn't result in 0. Let's take a simple case. Okay. So if you take this, okay, so let me change the color here slightly. Okay. Let me change the color here to something which is, which we have not used. Okay. Let's take this color. Okay. So let's take this 3 by 3. Right, this 3 by 3, right, this 3 by 3 is second from the top. So your first 3 by 3 is this orange. Your first 3 by 3 was this orange. You came one step down and you got this yellow 3 by 3, which will result the value in this cell. It will result in the value in this cell. Okay, so now let's see. Let's do the computation here. Right, let's do the computation here. You have 0. All three are zeros. Multiplied by these values will all be zeros. These values are 0. See, we are operating on this 3 by 3 matrix, right? All these are zeros, so you'll also multiply with zeros, you'll get 0. But here you have 255 now. 255 multiplied by minus 1 is minus 255 plus 255 multiplied by minus 2, right? Which is 255 into 2. 255 into 2 will be 510, right? So minus 510. Again, 255 multiplied by minus 1 is again plus minus 255. So what is the sum of all of them? You'll get a value of minus 1020, right? So you place a value of minus 1020 here. Fair enough, very simple. Now let's look at this cell. What happens to this cell? This cell will be generated by using this matrix. All are zeros, so this will also be 0. What about this cell? This cell is, you take this 3 by 3 matrix and convolve this and perform convolution on this 3 by 3 with this matrix. You again get 0. Right? What about this cell? For this cell, you will have to use, I've written too many grids here. Okay, let me see. For that, you need to use this matrix. When you use this matrix, look at the matrix that I'm circling. This 3 by 3 matrix, when you multiply with this, again, all zeros, 0, all zeros, all zeros, 255, 255, 255, multiplied by minus 1, minus 2, minus 1, component wise multiplication and addition. Again, I get minus 1020. What about this cell now? What happens to this cell? In this cell, I will use this matrix now. This matrix. Because again, see, look at it. You have all three zeros, 3 255s. So you'll again get minus 1020. Here also you'll get minus 1020. If you just repeat that operation. Okay, now let's see what happens here. Here the matrix that you'll have will be this matrix. The matrix that you'll have will be this matrix. Look at this matrix. Look at this matrix. Sorry. Okay. So all zeros multiplied by this 0. There are three 255s, but all of them are multiplied by 0, so no value. You have 255, 255, 255 multiplied by minus 1, minus 2, minus 1 correspondingly and added them up. So you'll again get minus 1020, minus 1020, minus 1020, minus 1020. What about this value? For this value here, remember for this value, what do I do here? I take this matrix. This matrix, look at it. I have 255, 255, 255, 255, 255, 255, 255, 255. Tongue twister there. Right? I multiply 255 with plus 1. I also multiply this 255 with minus 1. So they both cancel out. I multiply this 255 with minus 2, with plus 2, sorry. I multiply this 255 with minus 2. And when I add them up, they'll cancel out. I'll take this 255, multiply with plus 1. I'll take this 255, multiply with minus 1. When I add them up, they'll cancel out. These middle 255s are all multiplied by 0. So this value will become 0. Similarly, all these values also will become 0. Remember, we had a 6 by 6 input matrix. We had a 3 by 3 kernel. And our output matrix is 4 by 4. Why is it 4 by 4? Because I can't create 6 by 6 out of it. Right? How many 3 by 3s? Look at it. If I have a 6 by 6 matrix here, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. If I have a 6 by 6 matrix, in how many ways I can place my 3 by 3s on top of this? I can place here 1. I can again place here. I can place 3 times and 4 times. Right? I can only place 4 times. I can only place 4 times this way. And even here I can only place 4 times. First time, second time, third time, and fourth time. Because I can only convolve 4 times, or I can only perform convolution 4 times, because I don't have any pixels. Remember, I don't have any pixels above or on the side. Hence, my resultant after performing the convolution operator with the Sobel edge detector. And look at this image. I'll explain this image in a while for you. This basically says, okay, this is the output that we got. Let's understand this output in a second. Why is this the edge detector? That's an important question to ask, right? So let's take this image and write it down. Sorry, so Okay, we got this output. Okay, let's actually draw that output, the 4 by 4 output that we got. Right? This was the output image, 1, 2, 3. So I'll call this the input image, I'll call this the kernel, and I'll call this the output image. Okay, so the output image looked like this: 0, 0, 0, 0, minus 1020, 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 0, 0, 0, 0. This is 1020. Okay, so this is the image that you got. Now if you want to, because your grayscale image can only have values between 0 to 255. Okay, this is the minimum value in your grayscale image, and this is the maximum value in a grayscale image. So if you renormalize this image, right, by ensuring that the maximum value in the image, look at this. If I do it in such a way that what is the maximum value in this image? Zeros. Right? This is your output. This is the output that you got out of convolution. But if you want to look at it as an image, how does it look as an image? What is the maximum value here? 0. The maximum value that we want is 255. So we'll replace all zeros with 255. So what we are doing is simply basically normalization using minimum and maximum values. We know normalization of vectors, right? Using minimum and maximum values. Same technique we are using here. We are just normalizing elements of a matrix instead of elements of a vector. We know min and max normalization. What you're doing is simply normalization, right? And scaling, right? So you get 255, 255, 255, 255 here. You get 255, 255, 255 and 255. And the minimum value should be 0. And the minimum value is here. So what do you get? You get, so the output image that you get here, if I have to draw it as an image, okay, you will get bright areas in the center, 2 bright lines in the center, and everything above that will be dark. Because remember, what did we say? We said 255 are dark areas and zeros are light areas. So this area will be light looking area, this area will be dark. This whole area. So what you get here literally is, you'll get a region that is only 2 pixels wide, right? You'll get literally 2 pixels width area, which is light color. This is light color or white in color, and this is dark. And our edge was actually here, right? Our edge was actually here. So corresponding to an edge in your image, you're going to get 2 white lines. If you apply Sobel edge detector, what you're going to get is, if your image has a horizontal edge, if your image has a horizontal edge like this, it will result in the output image of course of a smaller size. It will result in an output image where there will be 2 horizontal lines, fully white lines, corresponding to the place where you have an edge. And everywhere where you don't have an edge, you will get dark region. Right? So this is for horizontal edge. So I hope you're convinced now that applying convolution using Sobel horizontal edge detector helped us detect an edge in an input image. And there is a lot of it. Sobel is just one type of edge detector. There are tons of edge detectors in image processing. You might wonder, okay, this has detected horizontal edge, but what about vertical edge? Imagine I have an image like this, a 6 by 6 image like this, where this whole region is light, right? And this whole region is dark. So here, what do you have? Here you have a vertical edge, right? Your Sobel horizontal edge detector cannot detect this is a horizontal edge detector. It can't detect a vertical edge. So there is something called a Sobel vertical edge detector. Vertical edge detector. And the way it looks is this. It's also a 3 by 3 kernel where it looks like this: +1, +2, +1, 0, 0, 0, -1, -2, -1. That's all it looks like. So given this input image, you can always write this as a 6 by 6 matrix, right? You can always write this as a 6 by 6 matrix, right? The way it look is this. You'll have all zeros here, right? I'll represent instead of writing 255 so many times, I'll represent 255 as dash. Okay, this dash here implies 255. Okay, because it's easier to write dash instead of 255. Okay, now I want you to do it as an exercise in your notebook, where take this image, apply the edge detector, vertical edge detector, convolve these two. Okay, and see what is the output that you get. Of course, you get a 4x4 output. You should get it in such a way that there are two lines of zeros here. So this is, you'll get 2 pixels wide zeros. Rest everywhere else, you'll get dark regions. You'll get dark regions like this, and you'll get 2 pixels wide light region. Exactly the way we have done. What we have done here, first you convolve, you'll get a bunch of values, and then you normalize using min and max. Here we got a horizontal edge of white pixels. There you'll get a, if you just repeat this, using the Sobel vertical edge detector or Sobel kernel. Okay, if you use the Sobel vertical edge detector kernel, it's a 3x3 kernel, right? So edge detection in image processing, in classical image processing, is done. So the summary of it is this. I wanted to do this as a notebook assignment. It's very, very simple. If you just play with it, you'll understand it, right? So there is a nice page for Sobel edge detector. So this is the Wikipedia page for Sobel edge detector. I'll show you a nice example what happens here. So if you take this input image, this is an input image, look at it. It has some horizontal edges, like this is almost horizontal. You have also some vertical lines, right? So what they've done here is they apply the Sobel edge detector, and the final result looks like this. Look at this. There is a horizontal region here. Corresponding to the horizontal region, you have thick white lines here. And here there is no edge. Look at this region. Look at this region. There is no edge here, right? That's why it's completely black. Wherever you have horizontal edges, you'll have lot of white color. If you have semi-horizontal edge, okay. Similarly, the way this picture has been created is this. They've taken this input image, they've applied Sobel vertical edge detector, okay, the Sobel edge detector kernel, right? They applied both GY. They get an image 1, let's say. They get, let's say, image 1. They apply GX. Okay, this is GX and this is GY. They get image 2. They sum up both these images now. So they got 2 images, right? One with horizontal edge detectors, one with vertical edge detectors. Right? They got 2 edge detectors now, right? They sum up both these images to get this resultant image. So in this image, you'll see both vertical edges and horizontal edges. Right? You'll also see some diagonal edges. Look at this. This is a diagonal edge. This is a diagonal edge. So what happens is, if it's fully white, the whiter it is, the more horizontal it is. The diagonal edges tend to be in a color of gray. Right? Look at this, is almost horizontal edge. It's fully clean white. It's almost horizontal. The vertical edges also are almost in the same color. And the more distinct the edges, look at this region. This pipe's color is very, very distinct from the background's color. This pipe color is very, very different from this above color. Because in this region, this pipe color is very, very distinguished from the previous color, you get a very white colored edge. While if you look at this region, there is a vertical edge, but it's not as pronounced or as contrasting as this. Because it is not as contrasting, you still get an edge here, but the edge is not very thick. It is of a color of gray. It's not thick white, right? So the more contrast there is like this, the more deeper white it will be. The less contrast there is. Here there is a contrast. There is an edge here. There is some contrast, but the contrast is not very, very deep. There is some contrast, but not like white and black contrast. And hence you still get an edge, but this is grayer scale. Look at this. These pixels are gray and these pixels are pure white. Right? This is a very, very nice example to understand convolution. Convolution is and in a nutshell, what are we doing here? We are using the operation of convolution for edge detection. And we know edge detectors are what are present in V1 or primary visual cortex. And we'll use convolution as one of the most important operations. And we'll use convolution as a core operator to design our convnets. Right? So all of our convnets will use convolution left and right. But remember, there is a nice analogy between convolution and vector multiplication, right? So what is convolution literally? In a nutshell, it is basically, if you're given two matrices, you're doing element-wise multiplication followed by addition. On matrices, you're doing this on matrices. When you compute W transpose X, suppose you have a neuron in MLPs, when you do W transpose X, suppose you have a simple neuron, let's say a ReLU neuron or something, you have X here and you have a bunch of weights here. What are you doing? You take each of the elements of W and X, you perform an element-wise product. This is nothing but dot product between W and X, right? What does dot product mean? It means element-wise multiplication. You multiply elements, corresponding elements, and then you sum. So convolution is nothing but a generalization of dot product, if you want to think about it that way. Convolution is a generalization of dot product, because what you have, even in dot product, you're doing element-wise multiplication and addition, but you're doing it on vectors instead of matrices. So a very simple way to understand convolution operator is, it's a very similar concept to a dot product. What is this? This is a dot product, right? It's very similar to a dot product, but done on matrices. So we are doing a element-wise multiplication plus addition. And this analogy of this relationship between a dot product, and convolution, I will revisit this when we learn the convolutional layer in a neural network. But if you think about mathematically, they are one and the same. They're basically element-wise multiplication followed by addition, except that dot product is done on vectors and convolution is done on matrices. Of course, there are also convolution operators on vectors. For this discussion, for images related discussion, let's just say convolution is mostly done on image matrices, and dot product is on vectors. But in a nutshell, they are the same. They're element-wise multiplication followed by addition. That's all there is. Okay. I hope in this video you have gotten a good understanding on how edge detectors work and the core concept of convolution, which is fundamental to the whole idea of convolution neural network.